Hey, I want to look at a class of problems known as optimization problems. Essentially, it's just a matter of taking what we know about extrema and applying it in real-world situations. Let's jump right into an example. This one is a classic. You have 500 feet of fence and you want to build the largest rectangular enclosure with one side formed by your barn. What should the dimensions be? And as we consider this example, we'll try to come up with a list of steps that you can take to solve any optimization problem. And the first step is really to read the problem carefully, and so we'll say that we've done that. I say that that's the first step, but really there's sort of a 0th step before that. These are word problems. Word problems terrify people. The step before that is take a deep breath, tell yourself you can do it, you can do it. Don't let it get to you, and then bravely forge ahead. And then the second step, if at all possible, draw a picture of the situation, often very, very helpful. So I've done that over here. Step 3, we're going to need to do some computations, and in particular some calculus, and so we're going to need some variables involved, and so we may as well label some of these sides. Maybe I'll call this side X, and I'll call this side Y. You could call them whatever you like. But if that side is X, then so is this one, so I may as well label that one as well. Fourth step, very important, state the objective. What are we trying to do here? I can't emphasize enough that you should actually really write this down, and in particular, you should use the word maximize or the word minimize. And I've given a couple of examples on the right. We might be trying to maximize the profit or minimize the cost. In this particular example that we're looking at right here, we're trying to build the largest rectangular enclosure. Well, largest tells you that you're trying to maximize something. And what is the largest rectangular enclosure? It's the one with the maximal area. And so as part of working out the problem, I should really write down those words, maximize area. That's my goal. And the beauty of writing down that objective so explicitly is that the next step is to express the objective in terms of the variables. Well, if I'm trying to maximize the area, then I need a function for the area in terms of my variables that I've introduced, X and Y. And that's very easy to come up with. It's the area of a rectangle. The area is X times Y, the width times the height, or the width times the length. In the end, I'm going to try to find a maximum of this area function, and we've only looked at local extrema or extrema of functions of a single variable, and so I sort of have a problem here in that there are two variables involved. And so that's my next step, is to deal with that problem. I'd like to eliminate extra variables so that I only have one left. And how do you do that? By what's known as identifying constraints of the problem. In other words, the problem tends to give us more information, some other information that will allow us to eliminate some variable. In this particular case, the other information or the constraint is that we know we have only 500 feet of fence. And how do we use that in this problem? Well, we look at where we're using fence. Well, there's fence here, and there's fence there, and there's fence there, and I know what all of those lengths are, and they have to add up to 500. And that gives me this equation that 500 is x plus y plus x, or 2x plus y. How do I use that to eliminate one of the variables? Well, I take that equation and I solve it for either x or y. In this case, it's probably easier to solve it for y. Not hard to solve it for x, of course, except that if you did, you'd end up with a fraction. There'd be a 1/2 y involved in your expression, and why work with fractions if you don't have to? And then I can take that expression for y equals 500 minus 2x, and substitute it into my expression for the area. The area is x times y, so it's x times 500 minus 2x, which after you distribute is 500x minus 2x squared. And now I'm in great shape to do some calculus. I have a function that describes the area in terms of a single variable. I'd like to find the extrema of that function. And to find the extrema, you take the derivative and you set it equal to 0, and you solve for x, and we easily see that the only critical point is that x equals 125. Now, that critical point could be a maximum or a minimum or maybe neither. It would certainly be embarrassing to do all this work and then find the answer that gave the minimum, the smallest possible enclosure. And so we should check that our critical point is indeed a maximum. In this case, it's very easy to tell using the second derivative test. The second derivative is -4 everywhere. In particular, at x equals 125, the second derivative is -4, which is, of course, less than 0. And so there's a relative maximum at x equals 125. It's rare that you really need this next step, checking the endpoints, and sometimes there aren't even any endpoints. But for example, suppose this problem had asked us to build the smallest rectangular enclosure. Well, our critical point here is a maximum, and we'd be looking for a minimum, so we would not yet have found it. And it really would have occurred at the endpoints being the possibility that maybe x is equal to 0, in which case y is 500, or y is equal to 0, in which case x is 250. And in both of those cases, the area is 0, and that would be the minimum. But as I said, usually the endpoints are not where we expect to find any truly interesting solutions. And then finally, there's the last step. Interpret the answer in the context of the problem. In other words, answer the question. For this example, the question is, what should the dimensions be? Well, we found one of the dimensions, 125, and in particular 125 feet. But we should also give the second dimension. And that's easy enough to do. We can use this constraint equation that we have right here that tells us basically that if we know one of the dimensions, how to figure out the other one. Plugging x equals 125 into that equation gives us that y is equal to 250. And so the answer to the question, the dimensions should be 125 feet by 250 feet. We should be a little bit more precise because that doesn't really tell us which side is which. And I can't describe it in terms of x and y's because those are variables that I made up. And so I'll say that the longer side, the 250-foot side, is the side that's parallel to the barn. And here we have the list of steps for solving an optimization problem written out a little bit more neatly. I'll post this on Blackboard for you. And in the meantime, you can have them sitting there while you try this problem. Find two numbers whose difference is 100 and whose product is as small as possible. You will not be able to draw a picture for this, but you should be able to do most of the rest of it. Take a few minutes and see if you can't work this out. Pause the video. When you're ready, start it back up. Okay, we've read the problem carefully. As I said, there's really no picture to draw, and so it's time to introduce some variables. What are we going to call these two numbers? You can call them A and B. You can call them Fred and Barney. I don't really care. X and Y is what I have chosen to call them. And our next step is to state the objective. Well, we're looking for the product to be as small as possible. And so our objective is to minimize the product. Expressing that objective in terms of the variables that we made up, well, the product is x times y. And now we'd like to eliminate one of those variables using some of the constraints of the problem. Well, the problem says that the difference of these variables is supposed to be 100. And that lets us solve for one variable in terms of the other. We get that x is equal to y plus 100. Substituting that into our objective function, that the product is x times y, gives us that the product is y plus 100 times y, or y squared plus 100y. We're now in great shape to find the extrema because we have the objective function in terms of a single variable. And so we can take the derivative, set it equal to 0, and find that there's a critical point at y equals -50. Once again, we'd like to check that that critical point is a minimum, and once again, the second derivative will confirm that it is. In particular, the second derivative is 2. 2 is a positive number, so evaluate the second derivative at -50, and you get a positive number, and that makes this a minimum. So this critical point is a relative minimum. In terms of testing the endpoints, well, x and y are real numbers. There are no endpoints. There's no biggest real number or smallest real number, so there are no endpoints to test. And all that's left is to interpret the answer in the context of the problem. The problem asks for two numbers. We've only found one of them, but this equation right here tells us how to find the other. And it's easy to see that the other number is 50, and that lets us answer the question. The two numbers are 50 and negative 50. Okay, those were optimization problems. You now know everything you need to know in order to do them. The next video that I post will have a couple more examples just so that we can get some more practice. See you soon.